In this video, we're going to return to the topic of volume, talk specifically about solids of revolution. Remember, in the last video we talked about general volume of solids. You have your solid placed along the x-axis from x equals a to x equals b, and you cut your solid perpendicular to the x-axis and get a cross-section. If you can find the area of that cross-section, which I'm going to call a of x, then you can find the volume of the solid simply by integrating that area function. And we're going to look specifically at solids of revolution, and in this case the area function is easy to figure out. So imagine you have a two-dimensional object, so it's in a plane, and you rotate around some axis in that plane. So maybe you have a two-dimensional picture in the xy plane and you rotate around the x-axis or the y-axis, and when you do that you get a solid, a three-dimensional object, and the cross sections of that is either going to be a disk, so filled in circle, or it's going to be an annulus, which is basically a washer, a circle within a circle. We'll see examples of those. It depends on exactly if the region touches the axis you're rotating around or not. So first off, let's start with the simplest case. We have a function f, and we're looking at the region between that function and the x-axis, and we're going to rotate it around the x-axis. Let's look at this picture. So here's an example. This is the square root of x. That's our function. This is shaded part is the region below that function. I'm going to rotate around the x-axis. So imagine the z-axis sticks straight out of the screen here, and I'm rotating around this x-axis, and it's going to look kind of like a little gumdrop lying on its side. Okay, this is the bottom, and then you got a sloping thing. Now Sage can do three-dimensional pictures of these the boundary surface. So it doesn't do the solid, it doesn't fill it in, but it does. See, here's this red line is the square root function, and if you rotate just the curve itself, the square root, around the x-axis, you get the surface, and then we want to fill this thing in. Now my video card freaks out if I try to manipulate this three-dimensional thing while I'm recording a video. I can't do both at the same time, so I apologize for that. If you want to click and drag, you can spin this thing around and look at it from different angles. If you turn your mouse wheel, you can zoom in and out on this thing. So imagine this little gumdrop on its side. Imagine it's all filled in. Okay, so this inside part should be all filled in. That's the solid. Okay, so that's the solid of revolution we're looking at in that example. So you take a cross section. In this case, you get a disk, a circle that's been filled in. Okay, we're going to cut this way. What does a cross section look like? It looks like a line segment. Let's say I cut right here at 2. So if x equals 2, I take my cross section. It's what you get by taking this line segment and rotating that line segment around the x-axis. Okay, so imagine just taking this line segment right between 2 and this curve, and take that line segment and rotate it right around the x-axis. So the disk we get by rotating that little line around there has area that's given by the formula for the area inside a circle, pi r squared. And what is the radius of that circle? The radius is given by the function. So if we look at this example, this is going to be the center of the circle. This is going to be the outside of the circle when we rotate around the x-axis. And so the radius is this distance from the center to the outside. That's the function itself. So we get pi times f of x squared is the area of that circle. That's the area of the cross-section. So the volume is the integral of that function. Okay, so in this example, when the function is the square root function, we just get pi times x and integrate it from 0 to 4, because that's where did 0 to 4 come from? I think that came from the problem. Yes, 0 to 4. So it depends on exactly how far along the x-axis you want to go. That will be given in the problem. And here's the integral in Sage. If you want to do it in Sage, it's not that hard an integral to do on your own. Okay, here's another example. Let's say I want to find the volume of the solid that I get from rotating around the horizontal line y equals 1. The region between the same function, f of x equals square root of x, and the line y equals 1 from 1 to 4. Okay, so now this is similar to rotating around the x-axis because x-axis is a horizontal line as well. But now I just chose this line, y equals 1. Okay, that's a horizontal line. Here's the square root of x. Here's the area between, or the region between square root of x and the line y equals 1. Okay, the key thing here is that this region exactly borders the axis that it's rotating around. There's no gap. If there's a gap in there, then we don't get a disk. We'll talk about that in a minute. Okay, so I want to rotate this curve around this line, and I'll get kind of a little cap looking thing. Here's the 3D picture. So this is the curve. You gotta remember, again, you got to think about this little cone being all filled in. Okay, so cross sections perpendicular to the axis of rotation, which in this case is this line y equals 1. If I take cross sections this way, I get a disk. The radius is not given by the value of the function, though. This axis of rotation is the center of the disk. So if I cut, again, let's say I take my cross section right here at 2, this is the center of my disk. This is the outside of the disk. I'm taking this little line segment and I'm rotating it around and I'm making a circle. And so the radius is the distance from here to the curve. And the function itself gives the distance from the x-axis up here. So I don't want this whole thing, I just want this little part, which is f of x minus 1. 1 because this is y equals 1 here. Okay, so the volume is the integral of pi times the radius squared. The radius is the function minus 1 in this example, and you get 7 pi over 6. There's the integral in Sage. Okay, how about if you rotate around the y-axis? Well, if you rotate around the y-axis, then you're going to take the region between the curve and the y-axis so that the region touches. Okay, so like this one. Here's a curve given by some function. We're going to take the region between that curve and the y-axis, and we're going to rotate it around that y-axis. It would be different if we took the region below the curve and rotated around the y-axis. There'd be a gap. Okay, imagine if we shaded underneath here instead of this part. There'd be a gap between the axis of rotation and the region over here. That would be a different situation we'll talk about in a minute. So right now we're going to take this part. So the region exactly borders the axis that we're rotating around. Okay, so in that case, if we have x as a function of y, so we're not having f of x here where y is given as a function of x. Now we need x as a function of y. We can get disks whose radius is given by that function. So we get the same formula. Okay, so I changed this to c to d because those are, say, the y-axis numbers. So y ranges from c to d, and then we have pi times the function squared, where now instead of an x function we got a y function. Okay, why is that? Okay, let's say we take a cross section here at y equals 1. This is the little line segment we get from that cross section. Take this little line segment and rotate it around here, and you get a disk. What's the radius of that line segment? It's this horizontal distance between the y-axis and the curve. Okay, that's not f of x. F of x gives you this vertical distance. Okay, given the x value, how far up do you go? What I want is, given the y value, how far to the right do you go? And that's why we need to change this function to a function of y that gives me x. Okay, now the problem might give you that y function, or it might not. Here I've given you the x function, and I'm going to have to convert that to, I'm going to have to solve for x in terms of y. Okay, so we're going to go from y equals 0 to y equals 2 along the y-axis, so that's this shaded part here, rotating around the y-axis. So the first thing is to take this y as a function of x and change it to x as a function of y. So this is what I start with. Remember, the function f of x gives you the y value. So y equals square root of x. I'm going to solve that for x. You just square both sides. That's it. You get x equals y squared. That's the same curve given x as a function of y. So the volume is y ranges from 0 to 2. It's pi times the function squared, where in this case the function is a y function. So y is the x in terms of y is x is y squared. There's y squared, and here's the integral in Sage don't forget to declare the variable y if you want to integrate with respect to y. And here's the picture. Again, you can spin this around and look at it from different angles if you want. This is the square root of x, or y squared, whichever way you want to think about that. It's rotated this way around the y-axis and makes this kind of, I don't know what that thing is. Imagine, again, this is all filled in. Okay, so in those examples, the axis of rotation was right along the border of the region you're rotating. What happens if there's a gap between your axis of rotation and the region? Well, if there's a gap, you don't get a disk for a cross-section. Instead, you get an annulus, plural annuli, or sometimes just called a washer. This looking thing. Okay, you got a big circle on the outside, you got a small circle on the inside, and the annulus is the stuff in between. It's kind of like a washer. Okay, what's the area of this type of thing? Well, you take the area of this outer circle and you subtract the area of the inner one. So if the outer circle has radius capital R and the inner circle has radius little r, then the area of your annulus is pi times the big radius squared minus pi times the little radius squared. Okay, so this is an example of an annulus. And then, of course, what's the volume of the solid? Well, if your cross sections are given by these annuli, you're just going to integrate this area function. Okay, so one way this can arise is if you have a solid of revolution that's formed by rotating around the x-axis or the y-axis or any other line, a region between two different functions. So let's start with rotating around the x-axis. I'm going to have a function f and a function g from x equals a to x equals b. Cross sections perpendicular to the x-axis are given by annuli. The outer radius is given by whichever function is on top, the bigger one. The inner radius is given by the other function, the one that's smaller. So let's just assume for now that f is always bigger than g. So f is always going to give you your outer radius. It's the bigger of the two, and g will give you the inner radius. So the area of that cross section is pi times the big radius. The big radius is given by the bigger function, minus pi times the smaller radius. The smaller radius is given by the smaller function, and the volume is the integral of that area. All right, let's look at an example. So here I have square root of x in blue, I have x squared in red, and I want the region between them. So here's the region between them. I'm going to rotate that around the x-axis, around here. Okay, so there's a gap there. If I take a cross-section, let's take a cross-section right here at x equals 0.6. What does a cross-section look like? It looks like this little segment rotated around the x-axis. What do I get when I rotate a little segment around the x-axis? Well, because there's a gap, there's going to be a gap in the middle, I'm going to get this segment rotated around in a circle, and what's going to come out is this looking thing, annulus. Okay, so notice that the function f, the square root of x, is on top in this window from x equals 0 to x equals 1. Okay, now normally you think of x squared as being bigger, which is true when x is bigger than 1, but with smaller than 1, x squared is actually smaller than the square root of x. Okay, so square root of x is on top. That gives us the outer radius. X squared gives us the inner radius. So the integral is integral from x equals 0 to x equals 1 of pi times the outer radius squared, where the outer radius is square root of x, minus pi times the inner radius squared. The inner radius is x squared. And the answer is 3 pi over 10. Here's the integral in Sage. Now, to draw this in Sage, I drew both curves in different colors. So the blue one is the g function, the x squared. That's the I don't know, inside, I guess. And then the outer one, the square root of x, I have that one in green. So the solid we want is actually between the green and the blue. I made the green a little bit see-through, so if you rotate this around, you can kind of see inside, like kind of like a jello. You know, this blue thing is the mold. Don't fill in the blue part, okay? I want to fill in between the green and the blue, which I can't rotate around and show you because my computer will freak out, but you can look at it if you want. Okay, now let's rotate that same region we just did around the line y equals 2. So this is another horizontal line. Y equals 2 is this guy up here. So you're going to rotate this region around this line. You're still going to have cross sections that are annuli. So that hasn't changed. What we do need to think about though is the inner radius and outer radius. Now this square root function does not give the inner or outer radius either one, and this one doesn't either. The inner radius is the distance between the center, which is the axis of rotation, and the function that's closest to that axis. So the inner radius is the distance between 2 and the square root of x. The outer radius is the distance between 2 and x squared. And what is that distance? Well, to find a distance between these two things, you just subtract. So the outer radius is 2 minus x squared. 2 minus x squared is this distance here. And the inner radius is 2 minus the square root of x. That's this distance here. So the volume is integral of pi times the outer radius squared minus pi times the inner radius squared. And this turns out to be 31 pi over 30. And here's the little kind of bracelet looking thing that you get when you do that. So again, you got to imagine looking at this part between the blue. Okay, the blue is kind of the inside, the green is the outside, and the solid is between the green and the blue. Alright, now what happens if you rotate around a vertical line? Either the y-axis or something else. Well, this one's going to be the vertical line x equals 4. So x equals 4 is this dashed line over here. I want to look at the region between 2x plus 1, which is this blue line, and x squared plus 1, which is this red parabola. Okay, x equals 0 to x equals 2. Alright, now, what's the outer radius? The outer radius is the distance between the axis of rotation and whichever curve is farther away. So you start at the axis and you go until you hit the further away curve. That's the blue one. So the distance between x equals 4 and this curve at 2x plus 1. The horizontal distance here. So I need horizontal distance. This 2x plus 1 gives me the vertical distance. So I need to convert all these functions from x functions to y functions. I need x in terms of y. Given y, okay, I'm going to take a cross section at some y, given y value. Given y, what is the horizontal distance? I need x. Okay? So, let's start with this one, 2x plus 1. I'm going to convert that from a y in terms of x type of function to an x in terms of y. So, subtract 1 from both sides, divide both sides by 2, and you get this. X is y minus 1 over 2. Let's go ahead and solve this one. Subtract 1 from both sides and take the square root. Now, I don't have to worry about plus or minus square root. All of these y values are positive, so positive square root is all I need. So x equals square root of y minus 1 is this parabola, and y minus 1 over 2 is this blue line. The other thing is I need to integrate, I'm integrating the y direction, so my limits of integration are not 0 and 2. Those are x numbers. What I need is the y numbers. And you can see from the graph y goes from 1 to 5, it looks like. Of course, I can figure that out by taking my x equals 0 and putting it into these functions. So I put x equals 0 in here, and I get 1. I put x equals 0 in here, and I get y is 1. When x is 2, if I put it in here, I get 2 times 2 plus 1 is 5. Here I get 2 squared is 4 plus 1 is 5. So when x is 2, y is 5. And both of these functions agree. They intersect here. If the functions didn't intersect at these ends, then there'd be a little even more issue here we have to think about. Maybe we'll have one of those later. Okay, so I converted all my functions to y functions. I converted my limits of integration to y numbers. So what's the outer radius? The outer radius is the distance between 4 and the line. So 4 minus the line gives you that distance. The inner radius is 4 minus the parabola. So there it is, 4 minus square root of y minus 1. So the volume is the integral from y equals 1 to y equals 5. Okay, these are y numbers. Pi times the radius squared for the outer radius minus pi times the radius squared for the inner radius. And it turns out the answer is 8 pi. Here's a picture of that thing. It's this kind of little, I don't know, volcano looking thing, truncated cone. Okay, I want to look at the region between sine x plus 1 and cosine x plus 1. Which one is which down here? The blue one is f, sine of x plus 1, and the red one is cosine x plus 1. So red is cosine, blue is sine. I want to rotate this region between those two curves around the x-axis from negative 3 pi over 4 to 5 pi over 4. Okay, so this thing. Now cross sections are annuli, except at this one place where it actually touches the axis, but everywhere else it's annuli. The issue here is, the outer radius is given by the function on top, and the inner radius is given by the function on the bottom. And the problem with this example is that the function on top changes. At the beginning, from negative 3 pi over 4 until here, which looks like it's pi over 4, we'll check that, the cosine plus 1 is on top. And right here, at this point, they cross, and the cosine ends up on the bottom. So the function that gives you the inner and outer radius, it changes. So we're going to have to break this problem into two parts. We'll integrate from negative 3 pi over 4 until pi over 4 and put the cosine on top, and then we'll do a second integral from pi over 4 to 5 pi over 4, and we'll put the sine on top. Okay, so how do we know they cross at pi over 4? Well, you'd have to solve the equation, find out where these two functions equal each other. When is sine equal to cosine? On this window. And, well, you might remember from the unit circle, at pi over 4, sine and cosine are both square root of 2 over 2. That's where they are equal to each other. They're equal again at these endpoints. 5 pi over 4 is so 180 degrees from this one. And back the other way would be that one. So that's kind of the opposite side of the unit circle. They're both negative square root of 2 over 2 at those points. We don't really care about those crossing points because that's where our region ends, and we don't need to worry about them there. Okay, so we'll go from negative 3 pi over 4 to pi over 4. Cosine's on top, sine's on the bottom. So the integral for that one is pi r squared for the outer radius, the one on top, minus pi r squared for the inner radius, the one on the bottom. Then we have a second integral from pi over 4 to 5 pi over 4, where now sine is on top. Sine plus 1 is on top, so pi r squared for the outer one, minus pi r squared for the inner one. And we just do those two separate integrals and get the answer, 8 pi times the square root of 2. Now, don't try to combine these because you can't just do one integral because the sign changes. Here we have a negative on the sine one, here we have a positive. Here we have positive on the cosine one, and here we have negative on the cosine one. So that flips around the sign. You mingle those together, you're not going to get the right answer. Okay? And here's the picture, what that kind of thing looks like. Again, it's the region between the outer blue and the the outer green and the inside blue. You got to think about the solid between those two. All right, what happens if you have a gap between the functions? So far in all our examples, we had the functions kind of crossed each other right on the endpoints. Here, in this example, we actually have a gap between the functions. We're going to think about what that's going to mean. So I want to rotate around this vertical line x equals 3. The region between the parabola y equals x squared, that's the red, and y equals 2x plus 4, that's this blue line. I'm going to take this shaded region here, I'm going to rotate around this axis. Okay, so there's a gap between the functions. And this part at the top, if I want to take cross sections perpendicular to my axis of rotation, x equals 3. So I'm taking cross sections this way. The cross section will be this little line segment here, rotated around the axis. So I get an annulus. What's the outer radius? The outer radius is given by the distance from the center, here at 3, until this line. Okay, so that's the outer radius. Inner radius is 1, the distance between 3 and 2. That doesn't change. This whole way, that inner radius stays the same. It's just 3 minus 2 is 1. Now, once you get to 4, that's kind of where this red one stops and the blue one starts up here. Here, the outer radius is no longer given by the distance between 3 and this line, because that line stops here. It's now, the outer radius is just 3. You go from the center all the way till here. So it's a constant 3 is the outer radius from y equals 0 until y equals 4. The outer radius is just 3. Inner radius goes from the center at x equals 3 until this parabola. So this part here is the inner radius. So the function that gives the outer radius and the inner radius, it changes when you pass this y equals 4. So we're going to have to do two integrals. an integral that goes from 0 to 4 and deals with this part, an integral that goes from 4 to 8 and deals with that part. Okay, so from 0 to 4, the outer radius is 3. The inner radius is the distance between 3 and this parabola. That parabola is, okay, remember we need to convert this to x in terms of y, so solve this for x. We get x equals square root of y. That's what we have here. 3 minus the square root of y gives us this horizontal distance between the center and this curve. That's the inner radius, and the outer radius is 3 from 0 to 4. So from 0 to 4, I got pi r squared for the outer radius minus pi r squared for the inner radius. Now from 4 to 8, the outer radius goes from 3 to this line. I need that line as a y function, so I'm going to solve this thing for x, subtract 4 from both sides, divide both sides by 2, and I get this, okay, half y minus 2. Subtract that from 3 to give the distance between the line and 3, and that's the outer radius. The inner radius is just the constant 1, 3 minus 2. So from 4 to 8, it's pi times the outer radius squared minus pi times the inner radius squared. Now be really careful here with your parentheses on this one. Okay, notice that this set of parentheses is for the squared. I need to square this whole thing. 3 minus the line is what gets squared, so I need parentheses around that. And then this subtraction applies to the whole line, so I need parentheses around the line because I'm going to subtract this. If you left off these parentheses, you'd only subtract the first piece and not the minus 2. We didn't have to worry about that so much over here because square root of y was just one thing. But here I'm subtracting 2 parts, so I need parentheses around that. Alright, so be careful. I mean, here you need one set of parentheses for the squared. You want to square this difference, 3 minus the square root of y. Okay, if you left those parentheses off, you would just square the square root of y. You wouldn't square the 3 part. Okay, so be very careful putting plenty of parentheses here with these differences. Alright, summarize. If you want to find a volume for a solid revolution, first I would recommend you draw a picture of the region you want to rotate and figure out where the axis of rotation is. If you're rotating around the x-axis or any other horizontal line, you're going to integrate with respect to x. You need your limits of integration to be x values. You need your functions to be in terms of x, so f of x. If you're rotating around the y-axis or any other vertical line, you're going to integrate with respect to y. You need your functions in terms of y, so like g of y or whatever it is, and you need your limits of integration to be y values. Okay, decide if your cross sections are disks or annuli, so it depends if there's a gap between the region you're rotating and the axis of rotation. If there's a gap, you get annuli. If there's not, you'll get a disk. And then once you have decided that, determine the radius for the disk, or if you have an annulus, determine both the outer and inner radii. Those might be given by the function itself. It might be subtraction. If you're not rotating around one of the x or y axes, you might have to subtract your function from whatever the axis is. Okay, so you have to think about it. And once you've got that up, then you can integrate the area function, either pi r squared or pi big R squared minus pi little r squared. Finally, if your answer turns out to be negative, okay, negative volume is not good. Usually that happens when you have an annulus question and you switch the inner and outer radii. So if you get a negative volume and you're dealing with annuli, try to switch the order of your subtraction. So you got the big R and little r backwards, usually. Okay?